Before proceeding to analyze circuits driven by sine waves, we'd first like to define the various terms within the sine function. Plotted here we have a sine function where our variable x of t can be expressed as x sub m sine omega t. T is our time variable, and we have two constants, x sub m and omega. For the first constant, x sub m, recall that the sine function can take on values ranging between plus and minus 1. Consequently, x sub m scales the magnitude of the sine function, and it tells us the maximum value or the peak value. This is usually referred to as the amplitude. The units of x sub m take on the units of whatever variable it is that is the sine wave. It could be current, it could be voltage, it could be any other variable of interest. The second parameter we're interested in is omega, and to explore that we want to define a few more terms. First of all, you'll notice that the sine function repeats every 2 pi. That time period is simply known as our period, or t, where t is defined as our period, and it has units of seconds. We usually don't refer to the period of a sine wave. What we refer to instead is the frequency, which is 1 over the period, or 1 over t, which is our frequency. The units for this are hertz, usually abbreviated Hz. Looking at our function now, you can see that when omega t is equal to 1 period, or omega t, that should be equal to 2 pi. We can rearrange this to write that omega is equal to 2 pi over the period. Normally we don't refer to it as the period, we'd prefer to substitute the period with the frequency, and so we can write that omega is equal to 2 pi times f. And this is a relationship between the frequency and what is known as the radian frequency of our circuit. The units of radian frequency is radians per second. The sine wave we have shown here can be shifted in time. We could shift it back to look something like this, where everything occurs earlier, but we have exactly the same shape as before. Now you can see it's going to go through what used to be the origin at some angle minus theta here. If we do that, our function will be exactly the same as the sine wave. It'll have the same magnitude, it'll have the same frequency, but now everything occurs at a different time. We can account for that by changing our equation to look like x of t now will be equal to the same magnitude as before, sine omega t, because it has the same radian frequency, plus it's got some phase shift. And we know that the sine function goes to 0 anytime the value inside the brackets is 0 or a multiple of 2 pi. And you can see now that this sine wave function will go through 0 earlier. This is our phase shift. Often we just refer to it as the phase of our signal, and its units are in degrees. We can see that adding a positive phase shift causes our sine wave to occur earlier than the regular sine wave. This means that we can say that this new function leads the other function, or we should specify two terms, leading and lagging. Leading implies that the function occurs earlier, while lagging implies that the function occurs later. We can say that x of m sine omega t plus our angle leads x of m sine omega t by our angle. Alternatively, we can say x of m sine omega t lags x of m sine omega t plus our angle by the same number of degrees. Lastly, we'd like to know how to compare two sine waves. If we want to compare two sine waves, we have to pay attention to a number of features. The first thing that's required to compare sine waves is that they must be of the same frequency. Otherwise, the phase will constantly change with time. The second point is that they must be either a sine or a cosine, because sine and cos give a 90 degrees phase shift from each other. Lastly, the amplitudes for both of them must be positive. A negative amplitude implies a phase shift of 180 degrees. You've probably noticed there's some curious notational units. When we write x of t is equal to x of m sine omega t plus our phase shift, the first term is in radians, while the second term is usually expressed in degrees. Well, it might seem difficult to switch back and forth between radians and degrees. It's actually a relatively simple way for humans to read what's going on in the function. And so we will continue with this conventional notation.